This is Mr. Stan coming at you with another physics video. This time we're talking about pulleys and basically things that have mass that are hung from strings or ropes that are hung around a pulley so that they're free to move back and forth, right? And we're going to assume that there's no friction in the pulley. And so what's going to happen, right? So if you've played with a pulley before, you know that the side that gets the most force is going to go down and the other side is going to go up. So here, for instance, in this picture, we have um, a pulley that has a 2 kilogram box on one side and a 4 kilogram box on the right side, right? So common sense would say that the box on the right side is going to go down and the box on the left side is going to go up. But how fast, right? And to answer that question, we're going to look at some of the forces involved and how to write equations and find the acceleration for systems like this. Okay, here's a free body diagram for each box. Each box has a force of gravity pulling it down and a tension force pulling it up. Notice for the forces of gravity that I've labeled them FG1 and FG2. And I've done that because those forces are different, right? There's different masses mean there's going to be a different force of gravity. But I did not label the tension forces FT1 and FT2. And the reason is that these tension forces are on the same rope, so they're actually going to be equal and opposite to each other, right? So the pulley changes the direction of the rope, but it doesn't change how tight the rope is, right? And so it doesn't change the actual tension force in the rope. And so when I put this into the equation, right, it's going to be tricky, and we can't do this the way we've done other problems because one box is affected by the other. Okay, so if there's a force pulling the 4 kilogram box up, that is in effect also pulling the 2 kilogram box down. And if there's a force pulling the 4 kilogram box down, that's also in effect pulling the 2 kilogram box up. Right, so just the normal Fx and Fy that we usually use is not going to work. What we're going to do is we're going to have an F net equation. We're just going to say F net equals mass times acceleration. And for F net, I'm going to list all the forces here, and I'm going to include the forces that are pulling the 4 kilogram box down as positive forces, and the forces that are encouraging the 2 kilogram box to go down as negative forces. Okay. So when I do that, I get this right here. So let's just look at these forces one by one. The force of gravity, Fg1, on the 2 kilogram box is pulling the 2 kilogram box down, so I'll make it negative. Now the tension force right above the 2 kilogram box is pulling this one up, so it's actually pulling the whole thing in the opposite direction. So I'll make that positive. Because when you think about it, if you're pulling up on the 2 kilogram box, the 4 kilogram box is going to go down. Okay, so that would be a positive force. Now the tension force on the 4 kilogram box on the other side is pulling the 4 kilogram box up. So if you imagine if you took your hand and grabbed the rope right above the 4 kilogram box and like yanked it up, you would cause the 2 kilogram box to go down. So this would be a negative force. It's in the negative direction. Finally, the force of gravity on the 4 kilogram box, Fg2, is a positive force as it's causing the right side to go down. All right, so we have this equation here. We're going to start putting numbers in. Remember, the force of gravity is just the mass times g, the strength of gravity, which is 10. Right, and we have Ft minus Ft, and then we do the same thing with the 4 kilogram box. Now notice something here, Ft minus Ft, right? As I said earlier, these tension forces are on each box are going to be equal to each other because they're from the same rope, right? So the tension force is the same. So those are going to cancel out, which makes the math a lot easier. Now notice for the mass on the right side of the equation, right? You have to ask yourself, what is going to actually accelerate? And it's not just going to be one of the boxes, but both boxes. So because both these boxes move together, you would add those masses together. Now, technically, you'd also have to add the mass of the rope, but we're assuming that that's so small compared to the mass of the boxes that we don't include it in the calculation. Okay, so you would do a just a little bit of algebra. You find that 20 equals 6 times a, and then divide by 6. That'd be 20 divided by 6, or 3.33. Okay, now here is another situation. This is sometimes referred to as an Atwood machine, where you have a pulley on a table, and one box is hanging there, and the other box is on the table. So let's assume, to make things simple, that there's no friction on the table. Right? What's going to happen next? Well, obviously the 5 kilogram box is getting pulled down by gravity. It's connected to the box on the table, and it's going to pull on that box. And because the box on the table has no friction, there's no force to balance out that pull, and so it's going to accelerate. So the whole thing is going to accelerate so that the box on the table moves to the right, and the box hanging here goes down. And we're going to call that the positive direction. Okay, and we're going to add the forces. Now I'm only going to add the forces that influence the motion of the system, either make it go down and to the right, or would encourage it to go up and to the left. So you notice the normal force on this box is not causing it to move left or right, and so I don't put it in the equation. Same thing with the force of gravity on this box on the table. Because it's not encouraging the system to move left or right, I'm not going to include it in our FNet equation. I am going to include this tension force that's on the 15 kilogram box, right? And I'm going to say that that's a positive direction that goes kind of like down the rope, right? If you can imagine, like the rope is like a river that starts here and goes down here to the ocean. Anything that goes down river is going to be positive. Anything that goes up river is going to be negative. Okay, so the second tension force is going the opposite way. So I'm going to call that negative, and so that's why you have Ft minus Ft. That comes from these two tension forces that are pointing in opposite directions. Okay, finally, the last force is Fg2, the force of gravity on this 5 kilogram box. And that's pulling this down, so I'm going to call that a positive force. Now, for the mass, right, first of all, the force of gravity is 5 times 10, because there's only one force of gravity that's actually influencing motion of the system, and that would be Fg2. So that's 5 times 10, and these tension forces cancel out. Now, as I was saying, what mass do we put right here? Well, we have to, again, think about what mass is actually going to be accelerating, right? And this 5 kilogram mass is going to accelerate, but it can't possibly accelerate without also accelerating the 15 kilogram box up here, right? So we have to add both of those masses together to get the total mass. And then doing a little bit of algebra, we get that the acceleration is 2.5, right? So much less than it would be. Remember, if you just cut the rope and let the 5 kilogram box fall, you get an acceleration of about 10. That would be in free fall, it would be a projectile, right? But the fact that you have a larger weight up here means that the larger mass means less acceleration. All right, hopefully that helped, and I'll see you around.